Mason Dell.
It's great. You know, like great for
Induction. So, our purpose is to investigate magnetic induction eddy currents by analyzing how a falling bar magnet interacts with comparing the observations to computational models. Results: experiment time is 1.25 seconds. Computational time is 0.97 seconds. Introduction to fundamental physical principles. Biot-Savart law describes the magnetic field limited by a constant electric current. Here you can see our equation that we have. Faraday's law, and the magnetic flux or magnetic field changes with time, the electromotive force is produced. And this is basically the equation we use. Newton's second and third law. F equals ma, and for every action is an equal and opposite reaction. Yes. Observed model. Initial conditions, bar magnet, and a stopwatch. Here you can see a picture of the experiment that we set up. You can see what it should look like from a diagram. My friend is everything else. Our observed model is data and calculation. Magnet equal 0.026 kilograms. Mu of magnet was 1.477 amps. So you can see from our trials the different values we got. You have tube, our length, width, inner radius, and height. We got all this measurement. And our average time from the trials. This is my computational model. So what I managed to code through GlowScript, the important parts. These are results I got when I ran the code. Here you can see the values in the graph, and you can also see the actual model itself. Our experiment time was 1.25 seconds. Computational time, 0.973 seconds. Some assumption, bar magnet acts as a magnetic dipole to apply Biot-Savart law. There's negligible air resistance. The only forces involved are magnetic and gravitational as well. Possible source of error with some like electronic and the magnetic device and surrounding could have affected forces. Friction against sides of tubes were not considered in calculations, and the stopwatch starting and ending may have been inconsistent during our recording. So here's our discussion. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So basically, due to Ohm's law, induced current in an aluminum tube would be much greater, create a greater magnetic force on the magnet and could counteract with gravitational force, which prevents it from falling. And what if holes or slots were cut in the tube? How would this affect the ring currents in your model? So induced current in a aluminum tube would be less if the holes would disrupt the current and the magnet would fall through that much quicker. Thank you for watching. This is my presentation.